In the previous video, we calculated the current for this RL circuit, and we found that the current was given by this equation, right? So now what we want to do is we want to express the current as a cosine function. So we want to express the current in this form: A cos omega t minus theta. Okay, so how do we do that? We can do that by just expanding this equation and noticing that what we get is A cos theta cos omega t plus A sin theta sin omega t. Right, now if you get that, we can compare these equations, and you should be able to notice that A cos theta is going to be equal to this value here, and A sin theta is going to be equal to this value here, right? Now if that's the case, what we can do is we can calculate, if you say this quantity, let's call it 2 divided by 1 is going to give you tan theta. So let me write it in blue. So tan theta will be equal to omega L over R. That means theta is given by tan inverse omega L over R. Okay. And similarly, if you want to calculate A, one of the ways of doing that would be to square this term and square this term and add it. So if you square this and square this, what do you get? A square cos square theta, A square sin square theta. Add them both, so you get A square, and then you can take a square root of that, right? So A square is going to be equal to this quantity square plus this quantity square. So let's do that. So what we have is R square Vm square over R square plus omega square L square square plus omega L Vm square over R square plus omega square L square whole square. And if you evaluate this, you should get Vm square root of R square plus omega square L square. Okay, so which means that our current I of t is given by Vm square root of R square plus omega square L square cos omega t minus tan inverse omega L over R. Let's just write this brackets here. Okay, so that's what our output is. Now let's make a few observations here. Now the first observation is that the input to our circuit, the voltage to our circuit, was a sinusoidal signal, and the current in our circuit is also a sinusoidal signal, right? And the frequencies are the same. And you expect that if a circuit is linear, then whatever the input frequency is, the output will also have the same frequency. In this case, the output is a current, right? What has changed? What has changed is the amplitude, and what has changed is the phase. So we said that a sine wave is defined by three characteristics, right? An amplitude, a frequency, and a phase. And when you input a sine wave to any linear circuit, what you'll have is you'll have a change in amplitude, you'll have a change in phase, but you will not have a change in the frequency of the signal. Another observation that I want to make is just the fact that this calculation is tedious and very difficult, isn't it? And that's for a very, very simple circuit where you have one resistor and one inductor. Imagine a circuit where you have several resistors and several inductors and maybe a few capacitors. It would be a nightmare to solve that kind of a circuit. So we need to work towards a more easier way of getting the solution to this circuit, and that's what we're going to do in the next few videos.